Hi, Mr. Green here. I'm going to take you through the next topic in our forces. This is on changes in momentum, following on from the momentum lesson, and the LO is to be able to calculate the force that acts on an object when the momentum of the object changes. Pause the video whilst you take that down as your lesson objective. Okay, some retrieval questions to start with. If you pause the video and attempt these 5 questions and restart when you'd like the answers. Okay, then question 1. What two things affect momentum? Mass and velocity will affect momentum. What's the equation to calculate momentum? Momentum is mass times velocity, or P equals mv. What are the units of momentum? It's measured in kilogram meters per second, or kgm/s. What's meant by the conservation of momentum? The total momentum before a collision happens is equal to the total momentum after the collision has occurred. And what's meant by an elastic collision? A collision where there is no net loss of energy that takes place in an environment where energy can't be lost. Okay, our learning outcomes today are to state the factors that affect the force an object experiences, to use the change in momentum equation, and to apply this knowledge to safety features in vehicles. Quick recap on momentum then, just to make sure we know what we're talking about. The momentum of a moving object is dependent on its mass and velocity. An object with a large momentum will be really difficult to stop. Momentum is a vector quantity, so it has a size and a direction. The equation to calculate momentum is as follows. Momentum equals mass times velocity. Momentum in kilogram meters per second, mass in kilograms, and velocity in meters per second. Okay, so some quick momentum revision questions. If you could attempt these questions, pause the video and restart when you'd like the answers. Question 2 and 3 require you to rearrange the equation, so make sure you're writing this down as you do it. Off you go. Okay, question 1 then. Momentum of a 50 kilogram mass at 20 meters per second would be 1000 kilogram meters per second. B, the answer would be 400 kilogram meters per second. C, 10 kilogram meters per second. And D, 0.12 kilogram meters per second. On C and D, you have to make sure you convert that mass to kilograms. Question 2, calculate the mass of the following objects. The mass with momentum of 50 kilogram meters per second, travelling at 10 meters per second. You have to rearrange the equation, and you'd come up with that mass is momentum divided by velocity, giving you 5 kilograms. Question 3, the velocity of the following object, a mass of 40 kilograms with a momentum of 30 kilogram meters per second. You rearrange the equation and you end up with momentum divided by mass gives you velocity, gives you 0.75 meters per second. If you struggled with that, please go back and have a look at the momentum video that's on our YouTube channel. Okay, so what happens when we change momentum? So if the resultant force acts on a moving object, the object will do 3 things. It will either speed up, slow down, or change direction. Now, if that happens, if we've changed any of those 3 things, the momentum of the object will change, because momentum is due to velocity of an object. If we speed something up, if we slow something down, we're changing its velocity. Velocity changes, momentum changes. Now, as this is physics, we can calculate that force that would be experienced, or the force that's needed to change that momentum. But we need to go back to Newton's laws of motion to find out how we can calculate that. Can you remember Newton's second law of motion? Please pause the video whilst you write that down. Okay, Newton's second law of motion is this. The acceleration on an object is proportional to the size of the resultant force and inversely proportional to the mass of the object. Now, this can be expressed as an equation which you probably know a lot easier. So if you could write down that equation, pause the video whilst you do that. Okay, the equation that can be expressed as is force equals mass times acceleration, F equals ma. So from this, we can state that the force that acts on an object changing speed is dependent on the acceleration and the mass of the object. Force is mass times acceleration. Keep that in mind. What's the equation to calculate acceleration? Okay, acceleration is the change in velocity an object experiences divided by the time taken for that change. In symbols, acceleration is delta v, remember delta means changing, delta v over delta t. Now in both the equations we've just seen, force equals mass times acceleration, and acceleration equals change in velocity over time taken for the change. Acceleration is present. That means we can combine these equations. We can replace acceleration in the first equation with this equation here. So let's combine these. So the two we're combining are force equals mass times acceleration, and acceleration is delta v over delta t. So in the first equation, replace acceleration with delta v over delta t. We get this equation, force equals mass times change in velocity divided by the time taken for the change, or F equals m delta v divided by delta t. Now we define momentum as mass times velocity, so this equation could now state force equals the change in momentum divided by the time taken for that change, or force equals delta p over delta t. Give you a quick example on how we'd use this equation. So what's the braking force on a car with a mass of 800 kilograms which slows from 30 meters per second to 10 meters per second, taking 30 seconds to do so? Pause the video and attempt that first. Okay, let's go through the answer. Force equals mass times change in velocity over the time taken for the change. In this case, the mass is 800 kilograms because it's the car that the change in velocity is taking place on. The change in velocity, well, it starts at 30 meters per second and reduces to 10 meters per second. So that would be 30 minus 10. And the time taken for that change is 30 seconds, giving us force is 800 times 20 divided by 30. 800 times 20 is 1600, so the force would be 1600 divided by 30, giving us a force of 533 newtons. Okay, use that information to answer these 5 questions. The 5th question requires you to rearrange the equation, so again, pen and paper and take your time. Pause the video whilst you attempt them and restart when you'd like the answers. Okay, question 1. Correct answer there would be 300 newtons. Question 2, 2000 newtons. Question 3, 937.5 newtons. Question 4, 8 newtons. Question 5. What's the change in momentum of a mass that comes to rest in 3 seconds requiring a force of 300 newtons? If you rearrange the equation, you'll get the change in momentum as 900 kilogram meters per second. Now using that answer, if the mass of the object is 40 kilograms, what must its initial velocity have been? Should have been 22.5 meters per second. Okay, so let's have a look at some safety features in vehicles. So why do seatbelts provide good protection in the event of a crash? So in both the examples we're going to look at a car that was travelling at 17 meters per second and crashes into an obstruction, coming to rest straight away. Now Newton's first law tells us that even though the car has stopped, the person in the car will continue to move at that same speed, continue to move at 17 meters per second, which is around 40 miles an hour, and they'll carry on moving at that speed until a force acts upon them. Now the person in the car has a mass of 80 kilograms, so use the equations that we know to work out the force that person would experience to stop. So without a seatbelt, the time taken for the person to stop would be really, really small, 0.2 seconds. Force is mass times change in velocity over time taken for the change, so that's 80 times 17, because the person goes from 17 meters per second to 0, and that takes 0.2 seconds. They would experience a force of 6,800 newtons, quite a large force. Now with the seatbelt, the time taken for the person to stop would be much bigger, and we'll look at why that is in a second. It would be 3 seconds. So force is mass times change in velocity over time taken for the change. 80 times 17, the person does come to rest again, does come to 0, so the change in velocity is 17, but we divide that by 3 now, giving us a much lower force of 453.3 newtons. Seatbelts are designed to stretch a little bit before stopping the person in the car moving. Now this increases the time taken for the momentum of the person to change. If we can increase that time taken, then we'll reduce the force required to make the person stop. So if we can stretch the time out that momentum is changing, we can reduce the force required for that. Helps us with this as well. Some areas of a car are designed to crush in a controlled way if the car is involved in a crash, and that's known as Crumple Zone. We can see there's rear and front crumple zones in the picture shown there. Now the crumple zones will again increase the time taken to change the momentum of the car. So the driver and the passengers involved in the crash would experience a much lower force because it's taking a little longer for that momentum to change, reducing the force involved. Safety features we've seen there all increase the time taken for momentum to change. If we can increase the time taken for momentum to change, we can reduce the force required to make that change. So this means a person involved in the momentum change will experience a much lower force. That means they're less likely to become injured as a result of the change in momentum because the force they're experiencing is much lower. So most safety features increase time taken for momentum to change. Okay, so with that in mind, we're going to be looking at some past paper questions now that deal with change in momentum. So each question, pause the video and attempt the question, then restart when you'd like the answer. So here's question 1. Pause the video and attempt that question. Okay, so question 1. The momentum of a moving object has a magnitude in kilogram meters per second and a direction. It is a vector quantity. A car being driven at 9 meters per second collides with the back of a stationary lorry. The car slows down and stops in 0.2 seconds, and the total mass of the car and driver is 1,200 kilograms. Calculate the average force exerted by the lorry on the car during the collision. So we'll use the equation we've been using for all the lesson. Force equals mass times change in velocity divided by time taken. Change in velocity is 9, the mass is 1,200, and the time taken is 0.2. So 1,200 times 9 divided by 0.2 is 54,000 newtons. Okay? Okay, attempt this question. Pause the video whilst you attempt that. Okay, so within 0.04 seconds of the car hitting the back of the lorry, the car driver's airbag inflates, and the airbag deflates when it's hit by the driver's head. Use the idea of momentum to explain why the airbag reduces the risk of the driver sustaining a serious head injury. Well, when we inflate that, it increases the time taken for the head to stop, which decreases the rate in change in momentum, which reduces the force that that person will experience. So just as we've been talking about previous to this, that's what you need to put on there. So it increases the time taken for the head to stop, decreases the rate of change in momentum, decreases the force that the head would experience. Okay, next question. Pause the video and attempt that. Okay then, so child with a mass of 35 kilograms falls off the swing and hits the ground at the speed of 6 meters per second. Calculate the momentum of the child as it hits the ground. Show clearly how you work out your answer and give the unit. So make sure you write down your equation, write down the data that you've put in there. So we're again on force equals change in momentum divided by time. Momentum is mass times velocity. 35 times 6 gives us 210. But our unit is kilogram meters per second. After hitting the ground, the child slows down and stops in 0.25 seconds. So get the change in momentum that you've just had. You've got the momentum going from what it was to 0. Work out the answer. Off you go. Force experience would be 840 newtons. Okay, there's the rubber tile used to cover. Explain how they reduce the risk of children being seriously injured. Again, we want to go on the same things. It increases the time to stop, it decreases the rate of change in momentum, and so it reduces the force the child experiences. Okay, I hope that was useful. If you want to review this video or any other videos on our YouTube channel, they would help immensely. Thanks a lot for listening. See you soon. Goodbye.